My name is Ozlem Belir. I'm from Turkey. I'm an architect and I take my degree of PhD recently. I'm not an academician. I have a small office and the other name is Elisa Ömer. She is the professor at the University of Architecture in Istanbul. I will present my research with these topics: introduction, method, experiment, results, and discussion. More than 1 billion people worldwide have various disabilities, of which 45 million people are visually impaired. According to World Health Organization 2012, architects must seek solutions for the accessibility problems that prevent visually impaired people from fully participating in social life. Vision is the most important manner for gathering environmental knowledge that is required for navigation and movement. Therefore, visually impaired presents a significant problem to independent movement. Mobility requires the ability to move around safely. In addition to vision, perceptions from other senses, ambient lighting, nearby objects, and environmental factors influence a person's movement. The aim of this research is to determine whether the design criteria of a space are also among the factors that contribute to the movement of the visually impaired. In this article, the term space design refers to the location, the characteristic of structural and sensory landmark, and quality of schematic design. A common solution offered for the movement of visually impaired persons is to provide with technological devices that support dynamic navigation. However, these devices often prohibit them from perceiving other sensory inputs, such as environmental sounds. These devices should not distract them from perceiving such sensory input, which can potentially be dangerous. We suggest that solutions that support movement and navigation within a space that rely on using other senses are desirable. Electronic devices that provide audio directions, navigations, and other assistance aim to support safe access for the visually impaired. However, the impact of the principles of spatial design should be considered when accessing the successful perception of spaces. A common approach to dealing with accessibility issues that stem from design and poor structural details is to offering retrofitted and technological solutions. Unfortunately, sufficient time and priority to accessibility issues is not given to the design phase. Instead, solutions are sought only after the construction is finalized. Furthermore, solutions that have further costs, which results in excluding the visually impaired who can afford these solutions. Lynch states that perceptions of objects are also strongly dependent on senses other than the vision, which refers to as legibility or visibility. According to whom, the more environment supports envisioning, the more legible it is. Furthermore, and if a space is legible, it can be visually comprehended by creating a texture of identifiable symbols. Lynch uses legibility as a reference to easily understand and remember a space. There are many research in the literature about legibility, so we can say that easier an environment forms a cognitive map in the mind of a visually impaired person, the more accessible it is. Lynch describes the landmarks, which he suggests as a point reference, as physical formations that can easily be identified. Sorrows and Gürtel categorize landmarks into 3 groups, including structural landmarks, which have an important role in the spatial settings. In this case, landmarks refer to those which the visually impaired are engaged with. Most people with a visual impairment have some partial vision that is useful. A visual residue can cover a large sector from the almost totally blind to the just legally blind person. This vision helps them acquire information about surrounding landmarks, hints, and obstacles. For example, visually impaired people can use residual vision to track a vertical or parallel route when following one or multiple navigation lines or move along a straight line. They can also make use of surrounding landmarks through their functioning senses. Besides residual vision, they can gain insight by smelling, hearing, and touching. The announcements accompanying traffic lights, the sound of water, the cashier sound at the supermarket, the smell of bread from the bakery, or the odor of waste bins are all useful landmarks for the visually impaired. The important thing here is that visually impaired people can identify the static landmarks. Such permanent landmarks, which may be referred to as sensory landmarks, constitute important reference points for the visually impaired. Landmarks considered as unique and memorable, as proposed by Rich, should be identifiable for visually impaired through sense other than vision. In this study, the hypothesis, the location and characteristics of structural and sensory landmarks in a spatial setting are important for the navigation of visually impaired people is examined. A visually impaired person is engaged with the landmarks in the space that surrounds them. Reliable and static landmarks identified by the person prevent the feeling of being lost. This supports the perception of the space and consequently the navigation within it. This work suggests that there is a need to investigate the impact of the space and environment design on the cognitive mapping ability of people with partial or total visual impairment. Method. In this study, an experiment was conducted in 2 shopping malls with significantly different layouts. The shopping malls were identified as public spaces. 14 people with partial or total visual impairment participated in this experiment. Specific routes were identified in the malls. The movements on these routes were mentioned. After they completed their routes, they were requested to draw and describe them in order to examine their cognitive method. Furthermore, an Excel map analysis of the layout of the space was conducted with space syntax method. During the evaluation, the subjects drew their perceived space with a spatial pen on a plastic embossing film that was placed on a geometry map. I gave you a sample. You can see if you want. In their drawings, they were spatially asked to indicate the landmarks on their sketches. Subsequently, the predicted movement of sighted persons in the same space is determined by use of the depth map software. From the results provided by this software, we utilize the connectivity and integration values. The axial map analysis predicts the routes which the sighted people are likely to use. Finally, the routes identified by the subjects in our experiment were compared with the routes predicted by the depth map. The trial included 14 adults with visual impairment, including 3 female and 11 male subjects, 4 with partial visual impairment, 4 with cognitive, and 10 with advanced impairment. 2 basic criteria were used in selection of subjects. The first one is the use of white cane with necessary training, and the second one is the ability to move independently. For the trial, 2 shopping malls with different layouts were selected. The first one has a typical simple and symmetric geometric layout, which we refer to as A. The second shopping mall has an asymmetrical and non-linear layout, which we refer to as K. Since through repetitive processes, people get familiar with their environment and organize the spatial knowledge with mental representations. For this reason, in order to assess the perception of space, subjects who have not previously visited these places were selected. While selecting the trial locations, less known and less accessible shopping malls targeting were chosen to minimize the use of memories. This figure shows the landmarks that were correctly perceived and identified only in shopping mall area, where 46% of landmarks were correctly identified in the shopping mall area. The second figure shows similar information for shopping mall K. In this case, the percentage of correct identification is higher at 67%. Some landmarks that were perceived during navigation were not accurately depicted in the drawings or descriptions. The subjects were more successful in shopping mall K in terms of accurately perceiving and identifying landmarks. The axial maps of the relevant floors for the shopping mall were drawn on that map software to study the impact of physical characteristics of shopping malls on human movement and the density of their views. The maps created with the software and numeric data is described. The software uses colors for the values, which are blue for low integration or connectivity and red for higher integration or connectivity. For the details, you can check from the paper. Results for connectivity and integration analysis created by the software from the axial map analysis for shopping malls are presented in the table. Finally, we independently superimpose the layout of correctly identified landmark with the connectivity and integration maps for shopping mall A and K. These variables, the relation between the successfully identified landmarks and the axis with the highest and lowest values. These are integration plans and discussing. The study has explored the impact of characteristics and location landmarks within space and their perception through multiple senses on the legibility of spaces for the visually impaired. Landmarks were found to be important for navigation and the subsequent legibility of spaces for the visually impaired. In addition to the identification of landmark, the ability to correctly place it is influenced by both the characteristic as well as the location of the landmark. The integration and connectivity values of the axis where the landmarks were located were inspected, which were determined to be related to the correct identification. Areas of high connectivity and integrity are considered to be high legibility and preferred areas to use. When these areas coincide with landmarks, they were also strongly preferred by the visually impaired, implying the correct area to place the landmarks. Landmarks were found to be significant in the navigation and the subsequent legibility of spaces for the visually impaired. When landmarks are considered the most easily perceived in these two shopping malls were smell and sound. In the trial, the smell of coffee and the sound of water from the food were most frequently identified. In shopping mall A, many subjects identified the smell of coffee, however only 67% of those who identified the coffee shop could accurately mark its location on the sketch. The results of integration analysis for shopping mall A indicate that the coffee shop is located on the axis with the lowest integration value. Assuming that people tend to use the paths with high integration and high connectivity values more often, that certain physical elements on these paths, such as landmarks, can be utilized when creating cognitive maps. Landmarks placed on axes with low integration values are not expected to impact the cognitive maps of the visually impaired. All subjects who perceived the pool in shopping mall K also successfully marked it on the sketch. In this case, the pool in shopping mall K is close to the axis with the highest integration and connectivity values. In the axis with the highest integration values, in shopping mall A, there are no structural elements other than colors. This explains why the coffee house, which was easily perceived by the visually impaired, yet not accurately positions on the sketch. In this case, the sense of smell is sufficient in accurately perceiving the space. We conclude that landmarks positively influence the legibility of the space for the visually impaired when they are accurately and statically located. This conclusion confirms the hypothesis. The characteristics and locations of structural and sensory landmarks within a space are important for the perception of a space and consequently for navigation of the visually impaired. Another significant observation was the fact that more people were able to identify landmarks in shopping mall K. Among the subjects, 12 were able to perceive 3 to 5 landmarks, whereas in shopping mall A, only 7 people were able to perceive 3 to 5 landmarks. The reason is because the landmarks in shopping mall K are located on the axis with high connectivity and integration values. Furthermore, it is difficult to identify structural elements and landmarks in uniform and symmetrical layouts. A totally impaired and frustrated participant stated, "I keep going around and come to the same spot in circular space to describe shopping mall A." Although the task of navigating and identifying landmarks, simple layout, which is a square area, may seem trivial, it turned out to be very confusing. When the participants were asked to mark the landmarks, which they identified during navigation on their drawing, they often failed. This suggests that in space with uniformity resulting from symmetrical layouts and lack of landmarks undermines the ability to navigate and develop cognitive maps. Nevertheless, the gallery space, which was perceived by 9 subjects in shopping mall A, and the columns which were perceived by 2 subjects were accurately marked on the plan by those who perceived them. Both of these landmarks are located on axes with high integration and connectivity values. The structure of sensory landmarks located on axes which have high integration and connectivity values clearly influence the cognitive maps of the visually impaired. In shopping mall A, the starting point of the route was perceived by 78% of the participants, however only 67% of them could accurately mark it on the sketch. In shopping mall K, the starting point of the route was perceived by 93% of the participants, all of whom accurately marked it on the sketch. The single line and street corridor of shopping mall K was effective in this outcome. The symmetrical layout and the route that starts and ends at the same point adversely influences the reading of the space by the visually impaired. Spaces that address multiple senses offers ease of navigation and independent movement of the visually impaired. In shopping mall K, the central roof of this shopping mall is open, resulting in sunlight and wind to create important sensory inputs. Furthermore, shopping mall K was more crowded than the other, resulting in a great deal of sounds of speech and footsteps. Visually impaired people tend to follow other people during navigation to ensure accurate navigation and to avoid any unnoticed structural dangers. It is therefore known that they feel uncomfortable in unpopulated spaces. Shopping mall K has an advantage in that regard. However, the sound of wind due to open air and loud music occasionally disturb the participants. A similar discomfort was experienced from the angle of sunlight, which resulted in a sharp contrast between lighted and shadow areas. This was particularly troubling for the partially impaired. Spaces addressing multiple senses offer an advantage in the legibility of spaces for the visually impaired. However, any poor design choices in details may adversely impact the legibility of spaces. In summary, legibility of spaces for the visually impaired is improved by the use of the right landmarks in the right places and by appealing to multiple senses. When the layout is designed with consideration of appropriate sensory and structural landmarks, spaces will be legible for the visually impaired. Furthermore, particularly for public spaces, the structural details, for example, stair details, height, must conform to international standards to ensure safe navigation for the visually impaired. This study is just the beginning to show architects' analysis with space syntax method could exist, and architects can do more researches just like this one. This study is a small part of a research and was conducted as an individual. It should be done comprehensively with universities and foundations also. Thank you for your attention.